see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe. Are we alone in the universe? Are we the only ones who look up at the stars and wonder, is anybody out there? Today, scientists quest for the answer in different ways. Some with massive radio telescopes, some with interplanetary and interstellar probes. If we find extraterrestrial life, what will it look like? Soft and squishy? Or will the first aliens we contact simply be self-replicating machines, their biological creators having died off millions of years ago? Some of the top scientists in the world probe for answers in The Search for E.T. It is the question that has kept many people awake at night, staring at the stars, pondering the possibilities. In a galaxy filled with 1 billion stars, in a universe filled with 100 billion galaxies, are we alone? The incredible vastness of the universe is difficult to comprehend, but here's a way to consider it. If you were to shrink the sun down to the size of a marble and put it on a sidewalk in downtown Manhattan, the Earth would be a pinprick about 4 feet away. Mars would be 2 feet beyond that. The nearest other star where we might hope to find intelligent life, Alpha Centauri, would not be 10 or 100 feet away. It would be in Washington, D.C., 230 miles distant. And another star might be as much as 7,000 miles away, in Rio de Janeiro. But if we ever did chance upon voyagers from these distant points in the cosmos, what would they look like? Would they be basically the same as us? Would they be fundamentally different? Could they be perhaps so strange and unusual that they are unlike anything we ever dreamed or dreaded could exist? Many believe the quest for extraterrestrial life must really begin with intense scrutiny of how terrestrial life, life on Earth, might have begun. And in the early 1950s, 2 chemists at the University of Chicago advanced understanding of life's basic chemistry dramatically. Nobel laureate chemist Harold Urey and graduate student Stanley L. Miller concocted a batch of primordial soup. They injected methane, ammonia, hydrogen, and water into a closed system of glass bulbs and tubes. These chemicals are thought to have been commonplace on early Earth.
If you put all of these things into a container and supply some form of energy to do some kind of reactions, what do they make? What kind of reactions go on?
Miller and Urey energized the mix with electrical sparks to simulate lightning. The results were, well, electrifying.
They got a brown sludge on the walls of their chamber, and when they started analyzing that brown sludge, there were lots of organic materials in it, and some of them were amino acids, some of the precursors, the building blocks for proteins.
Proteins, of course, are in turn the building blocks for life. The Miller-Urey experiment had demonstrated that the precursors of living organisms could have gotten their start from a chemical reaction. And such reactions aren't limited to Earth. Methane, ammonia, hydrogen, and water are plentiful on other cosmic bodies within our own solar system, and many scientists believe throughout the universe. Indeed, noted astronomer Carl Sagan, speaking of the Miller-Urey test, stated that no other single experiment had done more to convince scientists that life is likely abundant in the cosmos. But the presence of water was key. Such a chemical reaction could not have taken place without it.
Water is very good at dissolving materials, much better than many other liquids. And so you can dissolve all sorts of nutrients and chemical, products, things that can act as catalysts, things that go through the chemical reactions of life. So water is an excellent liquid for storing all of those chemicals.
On Earth, where liquid water exists, no matter how extreme the environment, some form of life also resides. It resides at ocean depths so great, sunlight cannot reach them. It resides in damp, rocky crevices, miles beneath the Earth's surface. And it even resides in the extreme salinity of an ancient California lake, with a salt content above 10%. That's 3 times the percent of salt in the ocean. But life on Earth also needs carbon, which was in fact the primary substance generated by the Miller-Urey experiment. All life forms as we know them consist in large part of carbon molecules.
Life needs some sort of ability to create long molecules that can store information. So carbon is amazing at building long molecules. So for example, the DNA molecule is sort of 1 billion base pairs long. If you stretched out a single DNA molecule from one of your cells, it would be a yard long from a single one of your trillions of cells. And so you need something that can store the absolutely huge amount of information that it takes to build a creature like a lion or a human or a tree.
But if life has taken hold elsewhere in our galaxy or beyond, would these conditions necessarily hold true? Would extraterrestrial life be water and carbon based? Would DNA shape intelligent life? And would the aliens look anything like us?
Maybe they would look a little bit like us, but that would be very, very coincidental. I mean, I just saw, a ground squirrel running behind a bush over here, and he inhabits the same planet I do. He's got DNA, probably 70% of his DNA is the same as mine. He doesn't look like me, so why would the aliens look like me? They probably wouldn't.
A scientist who has spent time pondering such questions and rendering speculative alien forms is Dr. Robert Hurt of the California Institute of Technology. Hurt is a visualization scientist who uses data returned by the Spitzer Space Telescope to render images of deep space objects and processes.
To try to find the best visual ways of explaining complex technical concepts, but through imagery. The planets that are being studied around other stars, the ways that stars and nebula form, processes going on in galaxies and the distant universe, all the way out to the edge of the Big Bang.
But for this program, Dr. Hurt has agreed to use known scientific data to render a speculative alien life form. For his alien world, he's chosen Jupiter. A real challenge, since Jupiter is essentially a giant gas ball.
Now here we have a place where there is no land to speak of. The atmosphere is made primarily of hydrogen and helium gas, though it's rich with organic compounds. And as you go deeper into the atmosphere, it gets warmer and much higher pressures. So as a kind of thought experiment almost, it was posed, what did you imagine living in an environment like that?
Referencing the only known model for life, living organisms on Earth, Hurt began by asking, what does life on Earth need?
You need sources of energy. You need the chemicals that life on Earth needs to build, the materials that it's constructed from.
On Jupiter, a primary source of energy is faint radiation from the sun, striking the top of the planet's atmosphere. And the only known source of chemicals for use as building blocks for life
are the organic compounds swirling in the Jovian cloud blanket. In considering a potential life form that could take advantage of both long-term, Dr. Hurt remembered an idea originally postulated by Carl Sagan in the 1970s, the notion of a sort of living gas balloon. Such a creature could remain aloft in Jupiter's atmosphere indefinitely.
Now, of course, there's a problem in Jupiter, that Jupiter's atmosphere is already made of the lightest gas we know of, hydrogen. So you can't really make a lighter than hydrogen balloon. So if you want a balloon to be able to float in Jupiter's atmosphere, it actually has to be a hot air balloon.
Hurt has invented an extraterrestrial organism that is really more plant than animal. A balloon-like plant inflated and kept buoyant by hot air.
Now, it's going to be really expensive in terms of biology to generate that heat yourself. So instead, if we imagine a creature that has a very dark skin, very thin, that allows solar radiation to heat the gases inside, you might be able to create something that will levitate, at least during the daylight hours, just by absorbing solar radiation.
At night, the plant would lose its heat source, but Dr. Hurt has allowed for this problem in the creature's design.
It also has a shape that is well adapted to act kind of like a parachute that can ride thermals when it's not able to heat its own gases and float like a balloon. So in the nighttime, it might sink down lower into the atmosphere, but by finding thermals, it could ride this up like a glider almost.
Time spent at lower altitudes would actually be beneficial for the creature. It's here that its food is most plentiful.
I've given it a kind of air root system that hangs at the bottom. When it sinks into the lower parts of the atmosphere, it can screen out and pull up some of those organic compounds we know exist in the atmosphere of Jupiter.
Of course, Dr. Hurt's creation of the Jovian balloon plant represents nothing more than an entertaining exercise in extreme, though science-based, speculation. But the possibility that some form of life might actually now exist on other cosmic bodies in our solar system is very real to many astrobiologists and geologists. And one such body is right next door to Jupiter, the ice-covered Jovian moon, Europa. 370 million miles from Earth, orbiting the giant gas planet Jupiter, is the most likely harbor for extraterrestrial life in our solar system, Europa. It's an ice-covered ball about the size of our moon, about 1/4 the size of Earth. Scientists believe the ice on Europa is covering a global ocean of liquid water. A convincing indicator is that Europa is a conductor of electromagnetic energy. It conducts the magnetic field generated by Jupiter.
This conduction is the signature, or we think it's the signature, of salty water inside Europa.
It's believed that the water layer on Europa might be as much as 100 miles thick.
Now remember, Europa is similar in size to the Earth's moon, so that means that even though it's a smaller body, it actually has twice the amount of liquid water of all of the oceans on Earth put together.
And of course, liquid water is what makes life possible on Earth. So scientists who make it their business to quest for extraterrestrial life are keenly focused on the study of Europa. But how could liquid water, which freezes at temperatures below 32 degrees Fahrenheit, exist on a moon 5 times as far away from the sun as the Earth? Europa orbits Jupiter in an elliptical pattern. Sometimes it's close to Jupiter, and sometimes it's farther away.
When it's close to Jupiter, it gets stretched by Jupiter's gravity. It's an effect that we call tides. And when it gets further away, it's stretched less. So it means that the body of Europa is continually worked.
Friction caused by this stretching generates heat, just as a rubber ball heats up when it's squeezed repeatedly. At the planetary scale,
This process is called tidal heating, and it creates enough heat, possibly, to keep H2O miles below the surface of Europa in liquid form. It also appears that this stretching causes fractures in the Jovian moon's icy crust.
Imagine if you were trying to change the shape of an egg. What would happen to the shell? The shell would crack. And so when we look at the surface of Europa, we see lines all over the place, which are almost certainly marking the locations of cracks.
The cracks appear to open and close frequently. And the potential for these cracks to allow subsurface water to interact with the surface has important implications for the possibility of life on Europa.
Water from the ocean is going to rush up into the crack. When it rushes up, it's going to freeze, start to freeze. A few hours later, when the crack closes, it's going to squeeze that slush up to the surface. And so wherever we see these lines on Europa, there are double ridges, one ridge lining along each side of the crack.
Most of the water, no doubt, sloshes back down out of the crack to the ocean below. It's likely to carry with it some of the building blocks for life that have seeped down from the surface. The top of Europa's ice layer holds oxygen. It's been separated from the H2O in the ice by charged particles in Jupiter's magnetic field.
In addition, the surface of Europa likely has organic compounds that come down from comets and bits of comets. So again, the surface has another ingredient that's important for life.
Dr. Richard Greenberg of the University of Arizona has graphically depicted how potential life forms might take advantage of the ecosystem created by a crack in Europa's icy crust.
Although the outer few inches would not be a good place for life to live because of radiation, once you go down just a few feet, life would be safe from radiation and also would get enough sunlight for photosynthesis. So you could have an organism at that level that photosynthesizes, and it would be connected to the ocean by this tidal water that rushes up and down every day.
A day on Europa is much longer than a day on Earth, about 3.5 times the length of an Earth day. Time for mobile organisms to venture into the fissure.
You could imagine other organisms that grasp onto the walls of these cracks and just exploit the flow of ocean water coming past them every day.
Even mollusk-like or jellyfish-like creatures might rise with the water into the cracks to take in fresh nutrients from the surface. Life in Europa's ice-covered oceans may also draw energy and nutrients from a place other than the icy surface. It's possible that residual heat at Europa's core has resulted in deep-sea hydrothermal vents. On Earth, such vents host multiple forms of exotic life.
What happens is that reducing water that's very hot and has lots of heavy metals comes out through the groundwater and is injected into the ocean itself. And there's a huge gradient in the chemical composition that life can feed off of. This chemical source of energy allows huge populations of bacteria and other very small life forms to exist. And there's a whole ecosystem, a whole food chain on top of that, leading up to fish and various worms that thrives at those locations.
In recent years, talk has arisen of sending a lander to Europa that could penetrate the ice and probe for life. But Europa expert Richard Greenberg believes that a lander might uncover signs of life without penetrating the ice.
If we send spacecraft to Europa to look for life, it might be pretty easy to find it, easier than people have realized. Most planning has considered how do we get through these miles of ice to get down to the ocean? How do you drill through or melt your way through? It may not be necessary if you can land in a place where liquid or ice has come up from the ocean recently, you might find signs of organisms in that ice. Or if you land really smart and find an active place, you might actually be able to sample real fresh oceanic water.
The risk in that case, some feel, would be contaminating the icy moon.
If we had microorganisms that stowed away on a spacecraft that landed on the surface of Europa, and those microorganisms found their way into the liquid water of Europa, we might later discover life on Europa that was life that we had sent there.
But elsewhere in our solar system, on another distant moon, earthly contamination isn't a danger. Life here would simply be too exotic. Since 2004, a NASA probe dubbed Cassini-Huygens has orbited Saturn, making multiple flybys of Saturn's largest moon, Titan. Titan is an enormous planetary body, the second largest moon in the solar system, 50% larger than the Earth's moon. If it wasn't in orbit around Saturn, Titan would be a planet in its own right. But most impressive of all, Titan, many scientists believe, could now, or at some point in the future, be an abode for life.
The geology is very much like Earth's. All the processes that we have on Earth, wind, erosion, lakes, volcanism, mountain building, impact craters, we find them all on Titan, and so Titan is very rich in terms of geology.
But at 840 million miles from the Sun, 9 times farther than Earth, Titan is beyond freezing. The mean temperature on its surface is almost 300 degrees below zero Fahrenheit. It is so cold, and water on the surface of Titan is frozen to such an extreme state, it behaves like rock. The rocks in this blurry photo taken by the Huygens lander are, in fact, water. It is so cold that hydrocarbons that are gases on Earth, such as methane and ethane, are in a liquid state on the surface of Titan. The Cassini flybys have spotted them.
We're seeing a lot of what looks like organic materials on the surface, and we're seeing large bodies of liquid, but it's not liquid water, it's liquid methane with possibly some ethane dissolved in it. There are huge lakes on the size of Great Lakes or small seas.
Astrobiologists are beginning to entertain the notion that organisms could have developed in those lakes.
Life could be very, very exotic. We have been thinking of life in terms of water and liquid water, but could there be life in liquid hydrocarbons? Perhaps. Life on Earth exists in some very difficult places that you wouldn't expect to find life. And we call these organisms extremophiles. That's because they can live under extreme conditions. For example, here on Mona Lake, very alkaline lake, and yet extremophiles have been found living here.
Another possibility is that life formed much earlier in Titan's history, when a great deal of heat from the initial formation of the moon remained. At that time, conditions on Titan would have been very similar to those on primordial Earth.
There's a lot of water there, there's a lot of nitrogen, a lot of other things. So you've got warm water, nitrogen, carbon. And we think some of these chemical processes that went on Earth to start generating the biological, pre-biological materials that later on would be incorporated into life, that may have started on Titan also, with the same kind of chemicals present in a warm environment.
Some think it's possible that if Titan's core is still warm, microbial life, at least, might still be present deep below the moon's surface.
living organisms have been found thriving in damp rock crevices 2 and 3 miles below the surface of the Earth.
Now, if you go deep down into Titan, and when I say deep down, I'm talking about 50 kilometers or 100 kilometers, maybe even a couple of 100 kilometers, just like Earth, as you go downward, it gets warmer. And it looks like probably at Titan there are materials mixed in with the water, such as ammonia, that can act as antifreeze. And we know this liquid water is a wonderful medium for all kinds of chemical reactions, including the reactions that generate amino acids and other prebiotic chemicals.
At present, though, close observation of Titan's surface is limited. The moon is cloaked in a dense atmosphere of nitrogen and methane. The Cassini probe is equipped with an infrared imager, but photos shot in a visible wavelength are often much more useful to analysts.
You have to somehow get around this opaque atmosphere that's obscuring your view of the surface. But to really see what's going on the surface, and notably to get a really firm idea of what is the composition of all these different things that we see on the surface, it turns out we're going to have to go down there close to do that.
The Huygens lander has touched down on the moon and sent back images. But the lander is not mobile.
When you land on a planet, of course, that brings tremendous advance in terms of science, but it's only one spot. So how much of the Earth would you know if you landed on the Sahara Desert, for example? You wouldn't see the kind of life that we see here.
One possibility for exploring vast expanses of the Titan surface would be to use a craft that works much like a hot air balloon on Earth. NASA's Jet Propulsion Laboratory is developing a balloon craft that would carry both imaging gear and equipment for studying the Titan atmosphere. Engineers consider a balloon the most stable platform for such a mission.
If a balloon loses its electronic control for several hours, no big deal. You can have something on board that senses that and tells the balloon, okay, close your ascent-descent valve and just go to a safe altitude and sit there until you get further instructions.
But while complex missions to far-off moons within our solar system are exhilarating and often return great scientific insight, the promise of discovering more than primordial extraterrestrial life is slim at best. The hope of finding intelligent, technology-producing life seems greatest when we look beyond our solar system to neighboring stars. While we may never encounter such life, for most scientists who study the universe, the notion that it exists somewhere makes perfect sense.
Life tends to evolve to become more successful, and one of the things that makes organisms successful, it seems, on Earth, is to become intelligent. So it seems quite plausible to me that there are creatures that have some sort of intelligence on other planets.
If one of those starts out 1 billion years before our solar system started out, and it takes that one 1 billion years longer to get to that point, well, they're at the right time right now.
And at radio telescope installations across the globe, we Earthlings are listening for them.
Oh, well, howdy doody, boys and girls.
We have been sending signals into the void for decades. Every broadcast on this planet, every FM radio wave, every television transmission goes out into the infinite for all of eternity. Could anybody out there be listening? And how long would it take our radio signals to cover the distance? Let's consider once again the analogy where our sun is a marble on a sidewalk in downtown Manhattan. Alpha Centauri, the closest other star, is a marble on a sidewalk in Washington, D.C. And a more distant star is a marble in Rio de Janeiro. A rocket launching from Earth, the marble in Manhattan,
would take 75,000 years to reach Alpha Centauri, the marble in DC. That same rocket would take 2 million years to reach the marble in Rio, a star 100 light years away. Fortunately, radio signals are much faster than rockets. They travel at the speed of light. So rather than taking 75,000 years, a signal traveling from the marble in Manhattan to the marble in DC would only take 4.5 years. A signal traveling from the marble in Manhattan to the marble in Rio would take 100 years to make the journey. Some of our earliest transmissions might now be getting close. But what about the reverse? Could intelligent alien civilizations be sending pings toward Earth to see if anyone is at home? Scientists on Earth are listening, using technology originally developed for studying distant cosmic phenomena, like exploding stars.
Many phenomena produce radio waves, and by studying the radio waves, you can also learn something about, what's out there and how it works. So using radio antennas to study the universe, that's an idea that goes back to before the Second World War.
The huge radio antennas used today, called radio telescopes, are so advanced and so incredibly sensitive, they can easily detect the energy of a flea hopping.
They're just big reflectors, right? So the radio waves that are coming down and falling on the ground all around us, on the whole Earth after all, well, some of those radio waves will fall on these antennas. So they bounce off that big mirror, then they get focused to a very sensitive amplifier, and then the signals are sent via cables back into a control room that's right nearby here, where they have sensitive receivers to sort of analyze the radio energy that's coming in.
Dr. Seth Shostak is a senior astronomer at the SETI Institute in Mountain View, California. SETI is an acronym that stands for Search for Extraterrestrial Intelligence. The SETI organization also uses radio telescopes, but not for studying natural cosmic phenomena.
The very same technology can also be used to look for signals that are made not by nature, but by, well, perhaps ET.
And how might one know the difference?
The kind of signal that we're looking for is what's called a narrow band signal. That is to say, it's just a signal that's at one spot on the radio dial, that it's at one frequency. That's the indication that the signal is made by a transmitter, not made by nature.
Of course, computers do the listening, not scientists.
We have these specialized receivers that do all the listening, and the computers are monitoring the receivers. So typically, we'll have receivers that monitor, say, 100 million channels at once. So if the computers see a signal that looks like it might be extraterrestrial, as opposed to a radar at the local airport or telecommunications satellite or something like that, then the computer will follow up on that signal, and if it's beginning to look like, yeah, this might be the big one, then it'll call us up and draw it to our attention. So we don't have to sit there and be bored all the time.
To date, no such signal has been detected. But the SETI Institute presses on faithfully. Rightly so, in the minds of many prominent astronomers.
Absence of evidence is not evidence of absence. So we can't say, well, SETI hasn't found anything so far, so obviously there are no other intelligent civilizations out there. No, we can't say that, and I support their continuing to look.
There are hundreds of billions of stars in our galaxy and hundreds of billions of galaxies in the universe. Just by sheer weight of numbers, I would be surprised if there is not intelligent life somewhere else in the universe.
With so many possibilities, how do SETI astronomers determine exactly where to focus their telescopes and efforts?
You want to pick star systems that have a good chance of maybe having a planet something like this one, so that there's a greater chance that you have intelligent life. But we don't really know very much about what kind of planets these stars have. So we just have long lists, literally millions of stars, relatively nearby our cosmic backyard, and we just work our way through them.
And what would happen if one day a SETI radio telescope picked up a signal that looked like it could be an alien transmission?
One thing you would certainly do if you picked up a signal is say, look, I'm not going to believe it until somebody else can see it as well, because, you know, there could be bugs in the software or hardware that are fooling you here. So what you would do is, at the point where you thought this looks real, you would call up somebody at another radio observatory where they also have antennas just like this, and tell them, look at that part of the sky over this range of radio frequencies, this part of the dial, and see if you find anything. And if it were confirmed at 2 or maybe 3 observatories, I think at that point you could safely go and have your press conference.
But what if our first contact with ET isn't through radio signals? What if ET arrives in a form we don't recognize? The first alien delegation could reach Earth in the form of machines, so tiny human beings cannot detect them with the naked eye.
Step forward.
You speak English?
We speak every language.
Since the 1950s, at least, science fiction films have consistently depicted potential alien beings as human-like.
Homo sapiens?
Slaves.
One particular alien form has been widely popularized in recent decades. UFO enthusiasts believe the U.S. military recovered bodies from crashed alien spacecraft in the 1950s. These alleged extraterrestrials are essentially frail miniature humans with oversized heads.
Little gray guys that usually have big eyes, they don't smile a whole lot. But they're always sort of soft, squishy, organic things. Maybe they don't have DNA, but they're biology. They're alive.
It's an easy anatomical form for human beings to comprehend and accept.
Is that what ET would really be like? Maybe. I mean, you know, it's a good guess. That's what we're like. But on the other hand, I think that within 100 years, we may invent thinking machines. And if we can do that, if we ever do that, the aliens might have done that a long time ago. Keep in mind, the universe is a lot older than the Earth is, so they've had plenty of time.
Hello, Kismet. You gonna talk to me?
While the notion of thinking machines might sound far-fetched, some futurists believe such machines are just around the corner.
We're shrinking the size of transistors on an integrated circuit. So every 2 years we can put twice as many on a chip, and they run faster because they're smaller. And this has been true now for decades. I can carry in my pocket today a computer that's thousands of times more powerful than the computer that all of us thousands of students and professors shared when I came to MIT in the 1960s.
Ray Kurzweil is convinced that the power and speed of computers will shortly surpass that of the human brain.
If you take the most conservative estimate of the amount of computation required to simulate the entire human brain, which is 10 to the 16th calculations per second, there are other estimates that are lower than that. Take the most conservatively high estimate, we'll have that for $1,000 by 2020. And we'll have it for $1 by 2030. We'll have that in a supercomputer, actually, within a few years.
Kurzweil predicts that in the near future, tiny supercomputers will be integrated into the human body to bolster some of its weaknesses.
We've already started. I mean, there are people walking around that have computers in their brains that have replaced a portion of their brain, like Parkinson's patients. And already these devices actually can download new software. So you can download new software to the computer in your brain from outside the patient. This is today.
It doesn't stop there. As technology marches forward, microscopic computer-driven machines called nanobots will be capable of performing a wide variety of maintenance tasks within the human body.
And we're ultimately going to be able to send these devices through the bloodstream, and we'll have billions of these blood cell-sized computers and little robots inside our bloodstream. They'll keep us healthy, and they'll be interacting with our biological neurons. So we go out to about 2030, the common man and woman will be part biological and part non-biological.
But perhaps Kurzweil's most radical prediction is that computers will ultimately allow human beings to transcend their biology,
shed their bodies altogether. Computers will scan the neurological functions of a person's brain and upload the individual's knowledge, experience, and personality to a storage device.
You'd have to, in real time, go inside my brain, probably with nanobots, blood cell-sized scanners inside the bloodstream, and send billions of them into my brain through the capillaries, and they would scan all the different neurons and gather every detail about me, all the neurotransmitters and ion concentrations and interneuronal connections, and every detail that makes me me. And I think that will be feasible. That'll take longer. You know, maybe that's 40 years from now or more. But we'll get to a point where you could actually capture every detail about a person and then recreate that personality.
The implications are, of course, staggering. Chief among them is the possibility of immortality.
You can back up your files. If the hardware dies, it's not the end of your files. You just copy them over to a new machine. The whole personality of your machine can be preserved. You can make another copy of it.
And the machines themselves will be intelligent enough to self-replicate and steadily improve their design.
We see self-replication in computers. For example, the software virus. That's an entity. It's not physical. It's just a piece of software, but it's actually able to copy itself. So someone can put out one software virus, and it's busy copying itself and then moving through the internet, and pretty soon it can be on 1 billion computers. So that's self-replication.
And of course, intelligent machines that are both immortal and much less vulnerable to radiation and other hazards of space could possibly survive long-term interstellar voyages. It's an argument that leads Ray Kurzweil and other futurists to believe that our first alien encounter will more likely be with intelligent machines than biological creatures.
Any civilization intelligent enough to make the trip here, they're not going to send big squishy creatures. They're going to send little nanobots, non-biological systems, and that's what we're going to do.
Intelligent or not, biological or not, the discovery of any form of extraterrestrial life would arguably be the most profound scientific revelation in the history of human civilization. Some would even argue it could have a profoundly positive influence on human interaction.
To me, I would think that this would really change our perspective as a people. I mean, if nothing else, just to give us the perspective that we are one species on one world in a universe in which we are unique for what we are. And if this doesn't provide leverage for us to get past some of our foolish differences, I don't know what will. I think ultimately it might be one of the best things that could happen for us.
There's even the possibility that contact with an alien civilization wouldn't cause panic in the streets, as some might predict.
At the proper moment, the invasion will be launched from our platforms.
I'm getting out of here.
Stay where you are.
I think humans are ready to meet aliens much more than they're given credit for. I think we're a lot more flexible and a lot more open to these things, and the idea that we'll tear ourselves apart in panic and society would collapse, I think that actually sells us way short.
But what if we never find the answer? What if we never hear any alien signals? Never meet any intelligent species outside of our own? Silence, in its own way, would be an equally profound response. It tells us that life is unique and that intelligent life is precious. It should be treasured and protected at all